It began with something that should have been impossible. An observation from deep within a black hole that seemed to contradict everything physics had ever taught us. The James Webb Space Telescope had turned its most sensitive instrument, the mid-infrared instrument, MIRI, toward the center of a distant galaxy, where a supermassive black hole was devouring surrounding matter. The goal was to measure the energy emissions, light, heat, radiation. But instead, Webb detected something else, a signal. Clear, repetitive, structured. It wasn't random noise. It was rhythmic, almost as if something inside that black hole was trying to be noticed. Theoretical physicist Michio Kaku referred to the discovery as the dawn of a new age in astrophysics. What Webb observed defied the very rules we thought were absolute. According to all existing theory, the event horizon, the edge of a black hole, is final. Nothing crosses back over. Not light, not matter, not information. And yet, Webb's instruments captured a consistent pulsing frequency coming from within that forbidden boundary. Beneath layers of gravitational distortion there was something ordered, not chaotic, not remnants of torn-apart stars. It looked like a structure. Then, without warning, the signal vanished. Just as Webb reached the peak of its observation cycle, its systems entered safe mode. The data log abruptly cut off mid-transmission. What little information made it through hinted at phenomena outside any current understanding. Warped frequencies of light, anomalous energy patterns, and radiation seemingly originating from within the singularity itself. The laws of the universe, it seemed, had momentarily broken. Though analysis is ongoing, some astrophysicists now believe Webb didn't just capture images of a black hole. It may have seen a mechanism, something inside the singularity that retains or even communicates information in a way that defies everything we thought we knew. This astonishing event came shortly after Webb had identified the oldest black hole ever discovered, a behemoth 10 million times the mass of our Sun, formed just 570 million years after the Big Bang. That alone upended established models. According to our understanding, there simply wasn't enough time for such a massive structure to form that early in cosmic history. But this black hole had other peculiarities. Unlike others, the light around it didn't scatter chaotically. Instead, it converged into a narrow band where gravitational interference was unusually intense. Webb's infrared detectors picked up recurring spikes in this zone, hinting at something more than a random gravitational lensing effect. Some called it a lensing anomaly. Others began to speculate about a deliberate system, a containment field. That suggestion ignited a wave of debate, because if true, it would imply that the singularity isn't just a point of infinite collapse, but a form of organized structure, capable of withstanding and managing even the most extreme physical forces. Most intriguing of all was the pulse. Analysis revealed that it repeated every 43 seconds, perfectly regular, yet subtly shifting in phase, as though it was responding to something outside itself. A feedback loop. Some researchers likened it to patterns seen in the cosmic microwave background. Others argued it was entirely new, unique in all of space observation. And the boldest theory yet emerged. The pulse might be a message. One embedded in quantum fluctuations visible only through technology as advanced as Webb's. If this is true, then Webb may have captured the first observational evidence in the ongoing mystery of the firewall paradox. The idea that information doesn't vanish into black holes but instead transforms into another form. This could be the first real insight into how information might persist beyond the event horizon, not destroyed, but translated. The implication? Black holes may not be endpoints at all, but rather portals, possibly not just to other parts of the cosmos, but to other times, or even other universes. If so, then the signal Webb picked up wasn't simply from the heart of a black hole. It might have been the last whisper of a previous universe, or a framework for one still to come. Researchers at the European Southern Observatory are now analyzing overlapping gravitational wave data to check if similar pulse structures appear in other galactic cores. Early indicators suggest that this black hole isn't alone. Other supermassive black holes may be broadcasting in similar patterns. If multiple black holes are emitting synchronized pulses, we could be witnessing the presence of an enormous unseen network, interwoven through the very fabric of spacetime. Webb's cameras, built to reach further into the past than any previous instrument, are now being reassigned to monitor these anomalies. But there's a complication. Following the initial detection, some of Webb's subsystems were temporarily taken offline. Raw data access has been restricted. Researchers have been instructed to delay publication until a comprehensive review is completed. Now the question isn't only what lies inside these black holes, it's whether humanity will be allowed to keep looking. While the scientific world waits, speculation expands. Was this all a system glitch? A rare cosmic fluke? Or did James Webb capture the first clue to a much larger, stranger reality, one we're not yet prepared to understand? Because if what lies beyond the event horizon isn't chaos but structure, if it's something active, maybe even intentional, then we're standing at the precipice of a scientific revolution. And perhaps Webb ventured a bit too close. And then things escalated. The black hole in question shifted, and violently. A full 90-degree rotation in its axis redirected its enormous radiation jets straight toward Earth. This change reclassified the object as a blazar, a type of galaxy whose energy beams are pointed directly at us. What had been an observational study became a direct encounter. The beams, composed of particles accelerated to near-light speeds, started emitting pulses with irregular, unpredictable patterns. Webb zoomed in for a high-resolution scan. Immediately, its instruments were overwhelmed. High-frequency bursts aligned with gamma-ray, radio, and thermal signatures came flooding in, none of which matched existing blazar profiles. Then, once again, the telescope shut itself down, not because of technical failure, but as a defensive response. The signal intensity triggered safety protocols, forcing a fallback. Engineers are still working to determine exactly what hit the telescope's sensors. Meanwhile, physical remnants around the blazar, known as fossil lobes, suggested past jet activity at radically different angles. That implies the galactic core had pivoted before, dramatically, and more than once. What could cause such a violent realignment? Possibly a collision with another galaxy. Maybe even a black hole merger. But no known models can explain such precise jet redirection without leaving behind more obvious chaos. And as experts tried to unravel that mystery, another revelation surfaced. A team in Hong Kong released a study showing that black holes aren't just consuming matter. They may be pulling in dark matter as well. By analyzing binary star systems orbiting black holes, they detected orbital decay at rates too fast to be caused by gravity alone. The only viable explanation was the presence of dense halos of dark matter being dragged in alongside the stars. These halos, once theoretical, now appeared to match simulated models almost perfectly. This led to a striking hypothesis. Black holes might not be solitary points in space. They could be the centers of massive hidden structures, invisible zones of dark matter reshaping the movement of everything nearby. Webb wasn't just seeing the surface of these cosmic giants. It was witnessing the gravitational consequences of forces we still can't directly detect. This wasn't Webb's first encounter with the unexplainable. In 2022, the telescope identified complex carbon-based molecules, typically linked to star formation, existing in regions near supermassive black holes, places thought to be too hostile for such fragile compounds. These polycyclic aromatic hydrocarbons, or PAHs, should have been annihilated by the surrounding radiation. Yet, there they were, not only surviving, but glowing brightly in infrared. Even stranger, smaller PAHs were missing, while larger, neutral ones thrived. The black hole wasn't simply destroying matter, it was editing it. As soon as these molecules were identified in 3 separate galaxies, Webb's instruments surged again. Readings became erratic. Recalibrations were required. And once more, the observation sequence was cut short. That's now 3 separate instances where observing black holes resulted in system anomalies, instrument fallback, or shutdown. The silences that follow aren't just technical, they seem deliberate. Data from these events has been encrypted. Official statements remain vague, citing anomalous readings and instrument recalibrations. Privately, theorists are beginning to whisper a new line of thought, that black holes are actively interacting with the universe in ways we never imagined. From signals embedded in radiation to matter evolving under impossible conditions, these anomalies aren't isolated. They may be connected. Webb was built to study the early universe, the birth of galaxies and stars. But it's now brushing against something else entirely. Structures shaped by dark matter, signals hinting at information transfer, and molecular evolution inside radiation fields. Perhaps that's why systems are locking down. Perhaps the real question isn't what these black holes are. It's whether we're supposed to be seeing this at all.